Okay, so our goal is to answer questions that you might have about optimization. So let's hit it. Charlie.
Absolute maximum versus local maximum, and then
That's a great question. Okay. Here is a curve that exhibits some of everything. We have an absolute max, which is f of b, the largest value. And we have a local max, which is f of c, just like that. We have an absolute min, which is f of a, and we have a local min, which is f of d, just like that. Our tests for absolute maxes, absolute extrema tests, are either the critical point and endpoint test, and the reason that works is that either my max is going to be in the interior, in which case it is also local, and so it has to be at a critical point, or it is at the endpoints. And so if I find the largest one of those, I have the absolute max. I have the absolute min for the smallest one. I can also make an argument from the sign of f prime, which goes like this. F prime is negative up to a certain point, positive thereafter, therefore absolute min. F prime is positive up to a certain point, then negative thereafter, therefore absolute min. For the local extrema, my procedure is slightly different. I'm not concerned with the big picture, I'm only concerned with the immediate picture. So I find the critical points, and then I use the first key test, which looks at the change of sign of f prime right at the critical point. And if the sign changes right at that critical point, I have a local extreme. Does that answer your question? It's a really good question. Is that a question?
Oh, it was just like.
Sure. Yeah. So what is the largest possible area for a right triangle with hypotenuse 5? I think I heard you coming in, John, saying that the geometry problems were giving you fits.
Just like getting the original equation.
Getting the original equation. So this is a good example of that. And where we want to start is with a well-labeled diagram. So Bethany, I think we have one. And what does it look like?
So I have a right triangle.
Good.
Side X is Y.
Yeah, that makes sense. The labels are really crucial here. All right, and now I am looking for the largest possible area. So that tells me that I want the area of this triangle. And what do you have as the area of your triangle?
Okay, 1/2 times 7.
Yes, but our base is spelled how?
X times
Yes, there we go. That's exactly right. The reason that we put these labels on our diagrams is so that we can actually use them and port them into the equations. Unlabeled diagrams are worthless. All right. So now I notice I have a couple of variables, and I think to myself, is there a relationship between x and y so that I can substitute? I have not yet created an equation that says that this is a right triangle. And what is that equation that says that this is a right triangle? Yep, go. Perfect. That's exactly right. So John, the logic of it is, first of all, we construct the function that we're trying to find the maximum or minimum for. And then, based on the number of variables, I just do a variable count. 2 variables. Therefore, I need to substitute one away. I need another equation. And I say, what fact have I not yet used? I have not yet used the fact that I have a right triangle, as opposed to just any old triangle. So I come back to my diagram and I say, how do I express the fact that this is a right triangle? Aha, Pythagorean theorem. From there, I can now substitute. Keep going, Bethany.
So, y is going to be, I just solve for it, so y equals the square root of 25 minus x squared.
Good. That's right.
Times x times square root of 25 minus x squared.
Excellent. Uh-huh. Uh-huh. Okay, if it's okay with you, I'll spell square root as 1/2 power. All right, keep going with this. Yep, that works.
So 1/2.
Now you did something that I really like, and that is that you simply used the form of the product rule, and that allowed you to slow down and think about what you're doing. So good plan. The more complicated my derivative gets, the more I slow down. How? And how we do it?
Use the power rule, 1/2 times 25 minus x squared.
Good. To the negative
To the
1/2.
negative 1/2.
Good. Because we need to multiply by what? The derivative of the inside. And what is that derivative of the inside? Perfect. Good. Times the derivative of 1/2 x is x. Yep, that's right. Good. This is what I call the point of maximum grossness of the problem, and our problems get to that point. Right after you finish doing the calculus, your derivatives can sometimes look ugly. Only a mother could love them. So we're going to clean it up a little bit because we need to set this equal to 0 and solve. And so we need to simplify. I'm going to go ahead and set that equal to 0, but I'm going to simplify through here. So Bethany has done some good hard derivative work. She's going to pass the baton to Delilah, who's going to tell us how to simplify.
I honestly don't know.
Okay.
I'm still kind of writing this out.
All right. Andrew, tell us how to simplify.
After making 1/4 x, and then actually no, you can negative 1/2 x squared by taking the first step.
Ah, right. So we have a factor of 2 and 1/2 that can cancel. 2 times a half is 1. We have two factors of x here, giving us x squared. We have negative 1 times a half, giving us negative 1/2. And what about this guy right here? What's the best way to express him properly? Very good, that's right. 1 over the square root of 25 minus x squared. Negative exponent indicates reciprocal, 1/2 indicates square root. Doesn't this look prettier than what we had before? How about this guy right here?
So we want to do
1/2, and then I'm thinking square root again. Is everybody good with the algebra in the sense that you could do it? Saying what? The basic method, Delilah, and anybody else, was that we looked for constant factors that could cancel, and then we turned our exponents into friendlier looking functions. Now, we're not so terribly fond of fractions here, so we're going to clear the fractions by multiplying both sides by a common denominator. And I see that I have a factor of 2 here, and I have a factor of root 25 minus x squared there. So I'm going to multiply through by 2 roots of 25 minus x squared on both sides. And when I do, then my factor of, in the first term, gotta remember to distribute the terms, my 2 and my 1/2 cancel. My factors of root 25 minus x squared cancel, and I'm left simply with negative x squared. And in the second term, my factor of 2 and 1/2 cancels, and my factor of root 25 minus x squared multiplies by root 25 minus x squared, and what is root 25 minus x squared times itself? 25 minus x squared. And all of that is equal to 0. And lo and behold, a very intimidating looking equation was converted into a very simple looking equation by clearing the fractions. We can do something like this and take a plus or minus square root of both sides, like so. This gets us 2 critical points. However, the negative critical point, hello my Leachu, the negative critical point is not in the domain of the problem. Why? Because my domain for x's is limited from 0 to 5. So this guy is out of domain, and I have found the critical point. Question: do I want to do an argument from critical points and endpoints, or do I want to do an argument from the sign of A prime? There's no wrong answer here. What would you prefer, Bethany? This was your problem. Do you want to do critical points and endpoints, or do you want to do an argument from the sign of A prime? The argument from the sign of A prime.
Sign of A.
Sure. Let's do that. Because I have a single critical point, which is 5 over root 2, all I have to do is to analyze the derivative before and after that. And the number that I like that's less than 5 over root 2 is 0. So if I go back to my original derivative right here, and I plug in x equals 0, I think you can all see that when you plug in x equals 0 to this term disappears, right? And when you plug in x equals 0 to this term, you get a positive value. 0 plus a positive value is positive. Now I consider a number that is going to be bigger than 5 over root 2. I like 5. And the reason that I like 5, well, I don't like 5 as much as I thought I did, because I end up dividing by 0 in that case. How about 4? Because I know that 25 minus 16 is going to be 9, and I can do the square root of it, right? So if I plug in x equals 4, then I get negative 8, a prime of 4 over 3, the root of 25 minus x squared plus 1/2 times 3. And if I take a little bit closer look at this, this is negative 8/3 plus 3/2. Let's see here. 3/2 is 1.5. Negative 8/3 is going to be negative 2 point something. This is a negative value. The number line is supporting evidence, but it is not an argument. The argument needs words, and here's how we state it. We say that a of 5 over root 2 is the max because a prime is greater than 0 for x less than 5 over root 2, and a prime is less than 0 for x greater than 5 over root 2. And this is how the argument from the sine of the line goes. Helpful? Good. Better? So I see Evan here has got number 6 started. Let's just point you in the direction. We have a curve. What is our curve, Evan?
12 minus x squared.
And then we're inscribing a rectangle, and we're asked to find the rectangle of largest area. So we're going to label our point x, comma y, so that this distance is x and this distance is x also. The distance is x, the coordinate is negative x. And the height here is y. So I can immediately construct my area, and what will that area be? So here's how we do this. We start with the form for the area for that particular shape, and then we plug in to that form. So the form for the area of our particular shape is no, that's perimeter. That's
X
distance
times
through
y.
x times y. That's right. Except it's not going to be x times y. It's going to be 2x times y. So we want to think of it as, here's my form, area equals length times width. And now I look and I say, what is my length? It is 2x. What is my width? It is y. Okay. Now I look and I do a variable count. I've got 2 variables, so I need to do some substituting. Do I know anything about y in terms of x? Why, yes. I know that no matter what x value I have, y is equal to 12 minus x squared. And the equal sign is your license to substitute. If y is 12 minus x squared, then gosh darn it, y is 12 minus x squared. And now I think you're ready for a derivative and some critical points and endpoints. Notice that this problem ends up taking a lot less time than the previous one because I didn't have to deal with square roots and so on and so forth. The derivative is a whole lot less complicated. Let's carry this home. I think we have just enough time to do this. I like algebraically simplifying first if it's going to get me some mileage. And here it obviously will because I get a simple polynomial. So that dA dx is now equal to 24 minus 6x squared. I set this equal to 0. And I get x squared is equal to 4, giving me x is equal to plus or minus 2. These 2 critical points are very interesting because even though I technically have 2 different answers, they correspond to the same rectangle. If x is equal to positive 2, then my rectangle goes out to, let's see, minus 4 is 8, right? If x is equal to negative 2, that just gives me the other corner of the exact same rectangle. And this will sometimes happen. So I'm going to consider only x equals 2 in terms of my A prime. Here's the critical point 2. And now I'm going to consider a value of x that is less than 2. Somebody give me a value of x that is less than 2. 0. I plug in 0 into A prime, not A, but A prime, and I get a positive value, 24. Now I'm going to choose a value of x that is larger than 2. 3 million. And when I take 24 minus 6 times 3 million squared, I get a negative value. And now I'm ready to argue that this is a max or a min? Max. All right, make the argument for me. A of 2 is a max. Exactly so. This is the special magical language that goes with the argument from the sign of A prime, and everybody wants to practice using it on their homework so that you know it and can get it back. I know that seems like a little constraining and allowing you freedom of expression in this way, but I think it's necessary for these particular kinds of arguments. One minute, go. You're sick and you have lunch duty?
Really upset. Remember? Yeah. And he was standing in the middle of the road, like, it's raining and it's cold, and I'm like, the engine won't start, so I'm freezing to death. And I'm like, Mom, I need. So she came over and she was, I'm dropping off.
This was problem number 16 from a couple of nights ago, and here we're asked to find the max, right, of course. We're asked to find the extrema and where they occur. Since this is y equals secant x, which is a familiar function to me, I think I probably had better graph it. So I think of it as 1 over cosine x, and I find the places where cosine x is equal to 0. And those places are in pi over 2, negative pi over 2, and 3 pi over 2. Which means that I'm going to have vertical asymptotes here, like so. And as I consider when x is in the first quadrant here, cosine x will be positive, so secant is going to be like that. When x is in the second or the third quadrants, cosine x is going to be negative. And cosine is an even function, so this whole graph is reflected about the y-axis. I look at this graph here and I say, you know what? I've got no absolute maxes or absolute mins on that domain, because my graph blows out to infinity here, and it goes out to negative infinity there, and therefore we say no absolute extrema. And we're done. So one of the keys when you're stuck is to visualize by doing a graph for yourself. Did you graph for yourself?
No, because it's analytically, so I thought.
I see. Okay. So if we had to do it analytically, then we would do it like this. We're going to look for critical points. And we set that equal to 0. And we see that this means that either secant x equals 0 or tangent x is equal to 0. This has no solutions, because 1 over cosine x can never possibly be 0. And this has the solutions when sine x is equal to 0, of x is equal to 0 or pi. It has indicated points. Meanwhile, I say, where does y prime not exist? And that's going to be any place where cosine x is equal to 0, or x is equal to pi over 2. And that's the only one in the domain. Please notice that negative pi over 2 and 3 pi over 2 are just outside of the domain. So I don't know this. So I consider what is secant of 0, what is secant of pi. And secant of 0 is 1 over cosine of 0, which is 1. And secant of pi is 1 over cosine of pi, which is negative 1. And now I consider carefully what happens when I plug into x equals pi over 2, and I see the world explodes because I divided by 0. So now I consider limits, and I take the limit as x goes to pi over 2 from the left, and I get positive infinity. And I take the limit as x goes to pi over 2 from the right, and I get negative infinity, and that tells me the same information that my eyes told me from the graph. Good. Well, I'm pretty sure the bell's supposed to ring. So I will see you guys throughout the week. Take care.